So, artificial intelligence have made remarkable strides, yet it often lacks the nuanced understanding that humans derive from common wisdom. Integrating these collective human insights into AI systems can enhance their learning processes and ensure safer, more reliable inputs. So we're going to explore the role of common wisdom in AI learning and how incorporating common wisdom can enhance AI safety, and then practical strategies for embedding common wisdom into AI development. So common wisdom encompasses the shared knowledge, experiences, and practice that society has developed over time. Incorporating this collective insight can help AI systems make more informed and contextually appropriate decisions. So AI may process data without grasping the underlying societal norms or values, leading to outputs that are technically correct but contextually inappropriate. So we could also enhance AI safety through common wisdoms, and then we need to integrate or embed common wisdom into AI development. All right, so understanding how AI learns can be illuminated by drawing parallel to human learning styles. Both AI and humans acquire knowledge through various methods, each with distinct characteristics. Supervised learning is like learning with a teacher. So its human analogy is similar to a student's learning under the guidance of a teacher who provides labeled examples and correct mistakes. AI, the AI model is trained on a dataset containing input-output pairs, learning to map input to the correct outputs. Example would be image recognition systems trained to identify objects by being shown images labeled with the names of the objects. And then unsupervised learning is about discovering patterns without explicit labels. So in this case, human analogy is comparable to an individual exploring and identifying patterns or groups without external guidance. AI applications is the AI models can analyze data without labeled responses, aiming to find hidden structures or relationships. So clustering customers based on purchasing behavior to identify distinct market segments. Then reinforcement learning is about learning from consequences. Human analogy is that we learn through try and error, where actions are shaped by rewards or punishments. Then AI applications is we can develop the AI agent that interact with an environment, making decisions and receiving feedback in the form of rewards or penalties, refining its strategies over time. So example is training a robot to navigate a maze by rewarding it for successful moves and penalizing it for hitting wall. These AI learning paradigms mirror human learning style, and it highlights the adaptive and multifaceted nature of both human and machine learning processes. Supervised learning in artificial intelligence mirrors human learning that involves explicit guidance, such as taking driving lessons or following recipes. In this paradigm, AI models are trained on labeled dataset, enable them to map input to specific outputs. For instance, in image recognition, models learn to identify objects by analyzing image tags with corresponding labels. Similarly, in medical diagnostics, models are trained on patient data labeled with specific conditions to accurately predict diagnosis. So supervised learning tend to have high accuracy when provided with high-quality label data. Supervised learning models can achieve significant predictive accuracy, making them effective for tasks like classification or regression. But the disadvantage of supervised learning include dependence on label data and scalability challenges. The necessity for extensive labeled dataset can be a significant limitation, as acquiring and labeling data is often time-consuming and costly. Training model on large datasets requires substantial computational resources and time, which can impede scalability. While supervised learning offers high accuracy through explicit guidance, it often presents challenges related to data labeling and resource requirements. Unsupervised learning mirrors human learning through observation, where individuals discern patterns and grouping without explicit instruction. So human can recognize social groups and identify shopping trends. So this is like the analogy for unsupervised learning. Human can observe interactions within a community and intuitively identify social circles or cliques based on behaviors and relationships. By noticing, in terms of identifying shopping trends, by noticing purchasing habit, individuals may detect emerging trends, such as a sudden popularity of certain products, without being told explicitly. So its AI equivalent is clustering customers, that AI can analyze customer data to group individuals with similar behaviors or preferences, aiding in targeted marketing strategies. And anomaly detection, AI systems examine data to identify deviations from the norm, which can indicate fraudulent activities or system malfunctions. So unsupervised learning can discover hidden patterns without the need for labeled examples, revealing insights that may not be immediately apparent. But the downside is the risk of misinterpreting noise and complexity in validation. Without guidance, AI might identify patterns in random data fluctuations, leading to incorrect conclusions. And assessing the accuracy of unsupervised learning outcomes can be challenging due to the absence of predefined label. So in essence, unsupervised learning enables AI to autonomously explore data, drawing inference akin to human observational learning, but it requires careful implementation to ensure meaningful and accurate results. Reinforcement learning is a machine learning paradigm where an agent learns to make decisions by performing actions and receiving feedback in the form of rewards or penalties. This approach mirrors human experiential learning, such as training a dog through reward and corrections, or athletes enhancing their performance through practice and feedback. So a notable example of reinforcement learning in AI is AlphaGo. Developed by DeepMind, AlphaGo mastered the complex board game Go by playing numerous games against itself, learning from each move to improve its strategy. This self-play mechanism allowed AlphaGo to explore a vast array of game scenarios, refining its decision-making process without human intervention. So it can adapt to dynamic environments. Reinforcement learning enables AI systems to adapt to changing conditions by learning optimal behaviors through continuous interaction with their environment. Again, reinforcement learning enables AI systems to adjust to changing conditions by learning optimal behaviors through continuous interaction with their environment. So it requires extensive trials because it adopts this trial and error approach. Achieving proficiency necessitates numerous iterations, which can be time-consuming and computationally intensive. In summary, reinforcement learning empowers AI to develop sophisticated strategies and adapt to complex tasks through experiential learning, akin to human learning from experience, from their interaction with the real world, through taking actions, making decisions, and receive feedback from the external feedback from the environment, either in the way of positive feedback that is reward or negative feedback that is penalty. Heuristics are mental shortcuts or rules of thumb that both humans and artificial and AI systems employ to solve problems efficiently. These strategies expedite decision-making by simplifying complex problem spaces, often at the cost of optimality. So here we are talking about some of the common heuristic strategies, including greedy algorithm, hill climbing, and simulated annealing. First, let's look at greedy heuristics. So the greedy heuristics is a problem-solving approach where decisions are made based on the most immediate short-term benefits without considering the broader context of future consequences. This method is prevalent in both human behavior and AI systems. So imagine arriving at a crowded parking lot, opting for the first available spot you see rather than driving around to find one closer to your destination, exemplifies the greedy heuristic. This choice offers immediate convenience, but may not be optimal if a closer spot becomes available shortly after. AI example is a navigation system. Navigation algorithms often employs greedy strategies to determine the shortest path from one point to another. For example, the greedy best first search algorithm selects the path that appears to lead most directly to the destination, evaluating nodes based solely on their estimated proximity to the goal. While this can expedite route planning it may overlook longer paths that are faster due to traffic conditions or other factors. So greedy heuristic leads to quick decisions by focusing on immediate benefits. The greedy heuristics enable rapid decision-making, which is advantageous in time-sensitive situations. but its downside is potential for suboptimal solutions. This approach, greedy heuristics, can lead to choices that seem beneficial in the short term, but are not optimal in the long run. For example, in the traveling salesman problem, a greedy strategy might involve visiting the nearest unvisited city at each step. While this reduces immediate travel distance, it doesn't guarantee the shortest possible route covering all cities. So the greedy heuristics offers a straightforward and efficient means of problem solving by prioritizing immediate gains. However, it's essential to recognizing its limitations, as this approach doesn't always yield the best overall outcomes, especially in complex scenarios where future implications are significant. Hill climbing is an optimization algorithm that iteratively makes incremental changes and updates to a solution, selecting modifications that improve the objective function with the goal of reaching a peak or optimal solution. This approach is prevalent in both human endeavors and AI applications. In professional development, individuals often seek to enhance their careers by making step-by-step improvements. This may involve acquiring new skills, seeking promotions, or changing roles to better align with their goals. Each decision aims to elevate their professional standing, akin to ascending a hill towards career fulfillment. In AI, hill climbing is utilized to optimize machine learning models. The optimization algorithm starts with an initial model and iteratively adjusts parameters or structures to enhance performance metrics such as accuracy or loss. For instance, in neural network search, hill climbing as implemented in gradient descent algorithm or gradient ascent algorithm can modify network configurations, i.e. parameters, to discover more effective architectures. This process involves evaluating changes and retaining those that offer improvement, thereby progressively refining the model. So it has the advantage of simplicity and effectiveness. Hill climbing is straightforward to implement and can efficiently find satisfactory solutions for problems with smooth or unimodal search spaces. Its iterative nature allows for continuous improvements without the need for complex computations. But it's susceptible to local optima. The algorithm may become trapped in local optima, where no neighboring solutions offer improvements, even though a better global solutions exist. This limitation necessitates strategies such as random restarts or incorporating stochastic elements to escape local optima and explore the solution space more broadly. So hill climbing offers a pragmatic approach to optimization by focusing on iterative and local improvements. While its advantages for its simplicity and directness, careful consideration is required to address its limitations, particularly the risk of conversion to a suboptimal solution. The evolution of AI reflects a transformative journey from rudimentary rule-based system to sophisticated data-driven intelligence. This progression mirrors human cognitive development, transition from rote memorization to experiential learning and autonomous reasoning. So in the early days of AI, rule-based system, known as also as expert system, rely on predefined rules and logical constructs to make decisions. These systems operate within narrow domain, applying specific if-then rules to derive conclusion. The rigidity of rule-based system made them inflexible and unable to adapt to new or unforeseen situations, as they couldn't learn from data or experiences. And machine learning introduces data-driven approaches. The advent of machine learning in the 1980s marked a paradigm shift, enabling systems to learn from data and improve over time. Algorithms such as decision trees, support vector machines, and clustering methods allowed AI to identify patterns and make predictions based on empirical data. These eras saw AI's application expand into areas like image and speech recognition, where learning from large data sets proved more effective than rule-based logic. And then deep learning mimicked the human brain loosely. So deep learning, which is a subset of machine learning, utilizes artificial neural networks with multiple layers to model complex patterns in data. Techniques such as backpropagation, pioneered by Geoff Hinton, has become instrumental in training deep neural networks, leading to significant advancement in AI capabilities. Deep learning has propelled AI to new heights, enabling advancements in natural language processing, computer vision, autonomous vehicles, and complex game-playing algorithms and robotic control. And then self-learning AI towards autonomous intelligence. The latest evolution in AI involves systems that can autonomously improve their performance without explicit external input, often refers to as self-learning AI. Methods like reinforcement learning allows AI to learn optimal behaviors through trial and errors, receiving feedbacks from their actions to refine future decisions. This approach is paving the way for AI to tackle more complex, unstructured problems, moving closer to artificial general intelligence. This evolutionary trajectory from rule-based systems to self-learning AI underscores AI's growing complexity and autonomy, paralleling the human journey from basic learning to sophisticated experience-based reasoning. So AI offers valuable insights into effective learning, adaptations, and decision-making strategies that can be applied to personal and professional development. So key takeaway includes we need to embrace data-driven decision-making and leverage AI for personalized learning and develop problem-solving and critical thinking skills and scale knowledge through AI integration. So first, we need to embrace data-driven decision-making and make informed choices. Just as AI systems rely on data to make accurate predictions, individuals can enhance decision-making by collecting and analyzing relevant information. This approach reduces reliance on intuition alone, leading to more objective and effective outcomes. And AI models improve through iterative feedback loops. Similarly, seeking regular feedback in personal and professional endeavors allows for ongoing refinement and growth. AI-powered applications can tailor educational experiences to individual needs, facilitating efficient skill acquisition and knowledge retention. And utilizing AI language models, such as ChatGPT, can provide interactive platforms for practicing new languages, enhancing conversational skills through real-time engagement. That is how we can leverage AI for personalized learning. And we can use AI to develop problem-solving and critical thinking skills. While technical skills are variable, the ability to identify problems and devise innovative solutions is paramount. AI can assist in generating new programming codes and do brainstorming and generate initial ideas. But AI insight is crucial for defining and addressing complex challenges. And we can use AI as a collaborative tool. Engaging with AI to brainstorm and refine ideas can enhance creativity and problem-solving capabilities, leading to more robust and well-rounded solutions. And we can also scale knowledge through AI integration. AI is capable of efficient information processing. It can analyze vast data sets to extract meaningful insights, enabling individuals to stay informed and make data-backed decisions swiftly. And AI-driven platforms offer coaching and self-improvement resources, providing personalized guidance to help individuals achieve their goals and unlock their potentials. By integrating these AI-inspired strategies, individuals can enhance their learning processes, adapt to new challenges, and optimize decision-making in various aspects of life.